I want to go over a little bit about gravitational fields and how exactly these work. Because although you may think that you understand the math, there's one thing that I don't think the textbook really captures, and I certainly didn't mention it earlier, and that is that a field is like, it's one thing to talk about the force, right? So I mean, the force that we talked about, the gravitational force. Well, if I use the pen, I suppose, is this one, right? So F, I usually write as big G equals GMM over R squared. Okay, so that's the equation for the gravitational force, and that's fine. Of course, in this equation, we have these two m's. So this grid here is going to be some area of space. So just to contextualize this, I'm going to say this circle here at the middle, this is the Earth. All right, boom, there it is. Okay, E for Earth. And what I want to do is I want to calculate what would the force of gravity, what would the Earth's force of gravity be on some mass if it were here, or here, or here, or wherever, any of these grid points in space. Now in this case, I don't know what the mass of the object is that I'm talking about. So this is where you would use the equation, the other equation that you saw, which was this one. Little g equals big G m over r squared. All right. So in this case, little g represents the gravitational field strength. And at the surface of the Earth, we know, of course, what this one is. This is 9.8, well, not one anyway, it's 9.80 meters per second squared, or newtons per kilogram if you prefer. But in the case of outer space, which is what this is representing, now this r squared value becomes a lot larger. So again, if this is, to some kind of scale, if this is the size of the Earth, then, we're starting to get quite large. This might be like several Earth radii by the time you get to here. So in this case, I'm not actually going to do the calculation, but what I want to do is just kind of represent this field strength here, little g, might be a vector pointing like that, and say with that magnitude, that size. But if I go away this far, maybe it looks more like that. So it's smaller. And then if I maybe go away this far, it looks like that. It's even smaller. And if I go away this far, then now I'm getting to the point where I can barely see it. So the idea is that this G is, this captures the magnitude of the vector, right? This big G m over r squared, that captures the magnitude of this vector, but really it doesn't capture the field part of it, which is that you actually have, when we talk about a gravitational field, we're talking about all of these different points in space, and all of these different points in space have a vector whose magnitude is calculated by, I didn't do that one very well, whose magnitude is calculated by this equation, but the pointing of it is, of course, into the Earth. So I don't know, I can spend a while doing this, but I hope you get the idea. All right. Now, one thing I just want to mention one thing here. In the video from last week, the presenter was talking about how if you want to write this big F G as a vector explicitly, then the way that they did it is they had a negative sign in front. So it was negative GMM over r squared. Okay, so this part here, excluding the negative sign, this part here just tells you the magnitude, so that's what we recovered up here. But then what the person did is they talked about this r hat vector, like this. And so for those of you who remember back to your vectors class, vectors in calculus class, this r hat vector is a unit vector, and the way it's defined in physics is, or in mathematics for that matter, An r hat vector is one which points away from the origin. So in this situation, Earth is our origin. So the r hat vector would be a vector pointing away from the Earth in whatever direction you were talking about. To show that this force is attractive, right? To show that the vector is actually the little g vector, the gravitational field vector is actually pointing inward, then we put this negative sign in front. So that basically flips this r hat vector around, and now it's pointing into the Earth. Okay, so that was like that was just a little bit of a, maybe a confusing thing. I don't know, maybe you weren't confused, but I thought it, could maybe use a little bit of explanation there. Anyway, this when you start introducing r vectors or r hat vectors, then you quickly start to talk about something called polar coordinates, which I'm sure you'll learn all about when you get to university. All right. So what I want to talk about now is the gravitational potential energy near the Earth's surface. So if you remember back from previous physics courses, we always talk about the gravitational potential energy near the Earth's surface, and we use this equation that the gravitational potential energy, which I usually write as E sub g, equals mg delta H. When I do this in grade 11, I usually talk about delta H. So technically this is also a delta. So the change in gravitational potential energy relates to a change in height. And generally speaking, the way we did it is that if you have something here like the ground, then we said that this is equivalent to 0 joules. And then you, I don't know, take a ball or something and you lift it up. Come on, pen. There we go. Okay. And you lift it up. Then you lift it up through some height called delta H. And so now this thing has more potential energy than it started with. Down here we say this is 0 joules. Up here this is some other number of joules. Again, it depends on what the mass is. It depends on what G is, but if it's on Earth, you know what it is. Anyway, so then we have the potential energy of this object is now positive, right? It's a higher number than it was before, because before it was 0. We always just say 0 is the ground. So this is one of these key things that I try and hit home in grade 11 physics, in that 0 can be wherever you want it to be, right? 0 is just a matter of convenience. And most of the time in physics, this is true. 0 is just a matter of convenience. You can reset it to be wherever you want to be, just like we did here. But it turns out that in some cases, you can't just do that. And so we're going to talk about a situation in a moment about where you can't just say, oh yeah, I want the surface of the Earth to be 0 joules, because in this case, in the case I'm going to talk about, that doesn't actually work. If I just take this equation though for a second here, so sorry, it's a bit of lag here, EG equals mg. If I just drop the deltas and I just write it as mgh. Now let's just say for the sake of argument, I was at the surface of the Earth. And so instead of talking about h, I talk about the radius of the Earth, which I will call r. So this would be mgr. And then if I plug in the equation for g, which was on the previous slide, then I have little m, capital G, big M over r squared, put brackets around this guy, and then the little r here. One of these little r's divides out with this, and I have an equation now that looks like this. E sub g equals big G, big M, right, mass of the Earth, little m, mass of your ball or whatever, divided by r. Okay? So this equation is going to show up in a second, but again, going back to this idea of setting 0 to, there's an actual definition of where zero potential energy is. This equation is going to pick up something extra, which is going to be pretty interesting. Okay. So Here's basically a graph that I took from your textbook. And what we've done here is we've said, okay, let's make a graph of the gravitational potential energy, that's the vertical, as a function of the radius, as a function of how far away we are from, let's say, the Earth. Okay, so in this case, there's a lot going on here, but this is the key. This is the one I want you to pay a lot of attention to right here. This is our definition. As our radius, as our distance between the objects, if you will, goes to infinity, as it gets really, really large, then the definition is that the gravitational potential energy goes to zero. So this line here actually represents, this is my 0 joules. Okay? Meaning I have to basically separate my two objects to an infinite distance for me to be at 0 gravitational potential energy. As soon as the two objects are close enough that they actually start attracting one another, and then the gravitational potential energy, oh, look at this, becomes negative, okay? So this might seem kind of weird. It's like, what in the heck can it mean to have a negative gravitational potential energy? Well, there's a few reasons why this might be, but I'm going to neglect talking about those just for the second. And I want to point out one little thing here. And this is that, let's say that this part of the graph is, now I know it says here objects in contact, but whatever. Let's just say that this part of the graph is where we're going to spend our attention. Okay, we're going to look here. Okay, so the idea here is that, let's say I have a ball, and it's not at the Earth's surface because that would be in contact with the Earth, but it's a little bit above the Earth's surface. And then I lift it a little bit higher above the Earth's surface. Well, in that case, at the higher position, I have more gravitational potential energy than I did before. Now, both of the numbers are still negative, but when I subtract this smaller negative number, when I subtract this larger negative number from this smaller negative number, then in actuality, I will have a positive result. Okay, so that's a lot to take in. So let me just put some numbers on this. Let's say that here I have, I don't know, negative 10 joules, okay? So at this position above the Earth's surface, my object has negative 10 joules of gravitational potential energy. And then here I have negative 5 joules. Okay, again, we're just keeping the numbers small just to make life simple. All right. Now again, in grade 11 physics, we wouldn't have done it this way. In grade 11 physics, we'd have said, let's take the starting position and call that 0 joules, and then up here we would have called that 5 joules. In other words, we'd have a 5 joule difference. In this case, however, if we're following this interpretation that this line represents 0 joules, then all my gravitational potential energies will be negative in this case. And so if I take my final minus my initial, which is how I get my change, right? So my change in gravitational potential energy is the same thing as whatever I have in the final minus whatever I had in the initial. And then in that case, the final, I have negative 5 joules. Good heavens. Minus negative 10 joules. All right, and I think you see where this is going. When I subtract a negative, it becomes positive, and so in this case, I have negative 5 joules plus 10 joules. So in actuality, my change in gravitational potential energy is positive 5 joules. So I do get the same result as I would have done if I had just used the old equation, right? The grade 11 formula, delta Eg equals mg delta h. The difference with this equation, the one I'm writing right now, really only makes sense when you're near the Earth's surface. However, this one, the one I've been playing with over here, the one that I've alluded to earlier, this one we'll be using when we're at like astronomical scales where we're talking about, the radii of the Earth, basically. I guess I just want to point out, though, that even though we've used a different equation, and we've kind of reformulated this so that 0 joules is at a distance of infinity, we still get the result that we do expect. The farther away we go from an object, right, the farther away we get from the Earth, that results in a positive gravitational potential energy. Sorry, a positive difference in gravitational potential energy. Derp. Okay, so I want to bring this back to the idea of the law of conservation of energy. So let's just say, for the sake of argument, I have an object at the surface of the Earth. So my object starts here at point A. Now, let's say this is something like a rocket, okay? All right, well, what this graph is telling me is that my gravitational potential energy will be this. And again, if I know what the mass of my object is, and I know what the mass of the Earth is, and I know what the radius of the Earth is, and I know g, then I can just plug and chug, and I get a number. But since all of these quantities will be positive, and I have a negative out front, then my gravitational potential energy will, of course, be negative. So that means that I'm over here. My gravitational potential energy is negative. All right, boom, just like that. Whatever, you get the idea. Okay, so, yeah, it's fine. Okay. All right, cool. All right, there we go. Get on there. Now, if my object isn't moving at all, then my total energy will just be the sum of my kinetic, the K is for kinetic, which right now is 0. My total would be negative as well. Now, that's not very interesting. However, in this case, if for an object that's not moving, that's just how it goes. Let's try something a little bit different. Let's say that my object is a rocket, and it's at the surface of the Earth, but it's fired its engines, and now all of a sudden it has a large kinetic energy. All right, so in this case, I'm going to get out my highlighter. I like blue. And so now my kinetic energy is like this. All right, so now I have this positive kinetic energy, right? If you remember, the kinetic energy, the formula for kinetic energy is EK equals 1/2 mv squared. All right, so mass can't be negative and speed can't be negative, and you're squaring it anyway, so this whole thing has to be a positive number. So that's why in this bar graph, I'm always drawing it in the positive. Now, so if these two things are exactly the same, if I have exactly the amount of kinetic energy that equals to my gravitational potential energy, then this positive number plus this negative number will just give me 0. And I'm just going to kind of draw that in there. So my total energy at the surface of the Earth is in fact 0, which is kind of bananas, but there it is. Now, some far, far distance away, let's say the rocket is actually able to escape from the Earth's gravitational potential, pull, right? So in that case, it's very far away. And if it's very far away, then by definition, its gravitational potential energy is 0. All right? The total kinetic energy, the total energy, this guy, is the same as this one was over here. So that'll be 0 as well. Whoops, that's not quite 0, but you get the idea. So if this is 0 and this is 0, then that means that my kinetic energy is 0 as well. So this is the condition where an object has just enough kinetic energy. This is almost like the Goldilocks scenario. It has just enough kinetic energy so that it's able to escape the Earth's gravitational potential well. All right, kind of an odd situation, but there it is. Now let's look at a slightly different situation. What if we actually didn't have enough energy? What if our kinetic energy was actually a little bit lower? So here, for example, okay? So if our object starts on the surface of the Earth, this number doesn't change. But let's say we have less kinetic energy, right? So our rocket isn't quite as powerful as the first one. Then in this case, my total is going to be negative, isn't it? Actually, I'll go with red. It's going to be negative, isn't it? Right? In this case, this number is negative, this number is positive, but if you add the two of them, you get a negative number. So this is going to be my total energy here. On this one, far away from the Earth, my total is still negative, right? That number doesn't change. There we go. Oh, okay. All right. Whatever. Okay, so that one's negative. And the gravitational potential energy is still negative, but it's not as negative as it was before. So that means that I'm up here somewhere, right? Maybe I'm up here, maybe I'm here at point C or something. So I'm able to escape this far, but that's as far as I can go. My kinetic energy is 0. My rocket basically doesn't have any more speed left in it. It's run out of fuel. And so now I'm basically stuck, right? I don't have enough energy to actually escape the Earth. This might be what you call a bound orbit. That escape speed is actually something that we can calculate. So in the case of the Earth, for instance, all we need to do is basically start off with the idea that, okay, my total energy, so E T, total energy, is equal to the sum of my kinetic energy plus my gravitational potential energy. All right. So in the first example that I did on the previous slide, I said that an object is able to escape. And it's able to escape if it has 0 total. In that case, in the case of an object that's moving, its kinetic energy is always 1/2 mv squared. And the gravitational potential energy, as I've been mentioning, is negative g big M little m divided by r. Okay. So in this case, since the left-hand side is 0, then I can say quite easily that I have g m little m over r equals 1/2 mv squared. And since I'm doing my algebra here, I want to look for any kind of simplifications. I see that this little m and this little m drop out, so that's kind of nice. And then if I multiply both sides by 2 and square root, then I get this equation. V equals the square root of 2g big M over r. All right. So what does that mean? This means that the escape velocity of any object, it doesn't actually matter what the mass is. The escape velocity or escape speed, I should say, the escape speed of any object that's trying to escape from the Earth is going to be a fixed number. It's quite amazing, actually. It doesn't actually matter if you have, a 1 kilogram rock, or if you have a giant rocket, or satellite, or whatever. It doesn't make a difference. If you want to escape from the Earth, you need a speed that's equal to this. And so if you go look up those numbers, then you can actually calculate it. You put all those ones in, and you get your calculator, and you get 1.12 times 10 to the 4 meters per second. Right? That's astonishing. That's 11 kilometers per second. 11.2 kilometers per second. Massive, 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 right? A lot faster than you're ever going to go in your car, for example. I don't care what you drive. All right, so there you go. So again, this is the escape speed. If you want to escape from Earth, you need to be going this fast. And if you don't go this fast, you're not going to escape. It's just how it goes. Okay, I want to briefly talk. This might seem like an odd sidebar here, but I don't know if you've seen these before in geography class or something, but there's something called a topographic map. And this is basically trying to answer the question of how do you represent something which is three-dimensional and yet projected into 2 dimensions, right? Like something that you can read on a piece of paper. So in this case, this is just a map of some mountain or something in Mali, in Africa. And so you can see that we have these mounds. And the most important thing is that we have these kind of shapes here, right? These solid lines, and they have numbers with them. They're really hard to read here, but these lines here, or these numbers rather, tell you the altitude of this line. So basically, if you were walking around on this line, you would always be at the same altitude, right? The same distance above the Earth. And ditto here, if you walked around this one, you would be at the same altitude, and so on and so forth. So this is basically showing you that this, again, if you read the numbers, they're really small, but they're going up if you go this way. This is basically showing you that this is the highest point on this map. I think that's right. Okay, so why do I care about that? Actually, excavation. Well, anyway, it doesn't really matter. The point is though that these are showing you different altitudes, right? Different elevations above the Earth's surface. So in the case of physics, we actually use something very similar to this. And this is the last thing I want to talk about today. It's the idea of something called gravitational potential. Now you might say, well, wait, I thought we've been talking about gravitational potential energy this whole time. And that's true. We have been. But this is actually slightly different. And the difference is very subtle, but it's going to make a little bit more sense when we talk about electric fields. So let's just say we're starting here at the Earth, right? Here's our Earth again. And if I want to draw in the gravitational field, then again, here are my vectors, like so. Now here's the thing. At these 4 points in space, because they're the same distance away from the Earth, the gravitational potential energy would be the same, right? It doesn't matter. Again, it doesn't matter what mass I'm talking about. Sorry, I'm just going to do it over here. So the gravitational potential energy would be negative g m little m over r. Okay, so the idea is once I know how big my satellite is or something, then it doesn't matter if it's here or here or here. It's going to have the same gravitational potential energy. It'll be negative, but that's fine. So to show that, you might choose to draw in a circle, because I guess it would be a circle here. I'm going to try my best to draw a circle. Kind of, okay. So this is basically showing that if you were anywhere on this red line, this red circle, that you would be at the exact same you would have the exact same gravitational potential. And likewise, if I were a little bit farther away, maybe at the next nearest neighbors here, and then anywhere on this one, you would be at the same. Well, I didn't draw that very well. Well, you'll have to forgive me. Oh. All right, so this one, you would be at a very negative gravitational potential. This one, you'd be at a slightly less negative gravitational potential. This one, you'd be even less negative gravitational potential. Oh, I'm really botching this one. That's okay. They don't pay me for my art skills. All right, and so on and so forth. So the idea is the farther and farther you get away, your gravitational potential is dropping off. Okay, so again, these are what are known as equipotential field lines, which is basically saying that if you are on this line, then your equipotential lines, not equipotential field lines. You're anywhere on this line, then your gravitational potential energy is exactly the same. If you're anywhere on this one, your gravitational potential energy is exactly the same. And to calculate that gravitational potential, you're going to be like, well, it's the same, isn't it? I never know what to use for this one. I'm just going to skip it. But anyway, I guess I'll call it phi. That's probably wrong, but that's fine. So in this case, it's negative g m over r. Again, there's no little m here, because the mass of the object that's sitting here is irrelevant, at least as far as the gravitational potential is concerned. All that matters is the mass of the Earth in this case. Anyway, Okay, so I went a little bit farther afield there, but I wanted to bring in this idea of gravitational potential and these equipotential lines because they're going to make a lot. It's going to make a lot more sense and be a lot more relevant when we talk about electric fields next week. Okay, so I just want to bring that up now, and then when we get to next week, hopefully this will make a little bit more sense now that you've seen it. Well, I guess we'll find out. Anyway, thanks for watching. I'll see you later.